The first continuous system that we'll look at is the simplest of them, and it is going to be a vibrating string. The general picture for a vibrating string is going to be a string that has a pin at this point O and then pinned at the other side as well. And in general, it can have some loading, some forcing function acting on its entire length here. And that forcing function can change as we go along the length x, and that forcing function in general can change as a function of time. So the forcing is going to be a function of both space and time. And that is going to mean that the deflection of the string, we're only going to be considering the vertical deflection along this z-axis, and that vertical deflection we are going to call w. So that w is the vertical deflection or vertical displacement. And that can also change in both space and time. And the angle that w makes with the horizontal, this del w del x, is going to also be called theta, and we'll use those interchangeably. So in treating this like a continuous system and not a 1 degree of freedom system like some of these types of problems we looked at before, is that just because we know the vertical deflection of one point on the string does not mean we automatically know the vertical deflection of all points on the string. They are going to move somewhat independently of each other, and that's how we're going to be deriving the equation of motion for this continuous system. So what we're going to do is we take this entire string and let's just look at a small differential element. So I'm just going to take a snip of it between these points A and B, and I'm going to say I'm taking a very small width, a differential width that is the width of dx. So taking that very tiny piece and moving down to this lower picture, we're going to blow that up and look at the free body diagram of this differential piece of the string that we are going to be taking. So what we can look at here is we're taking just a very small section of this forcing that's acting on it. So f of xt acting only along this portion of the string. And we're going to say and allow for the string to have a non-constant tension. So we're going to say on this left side, coming out normal to that surface of the cut, we're going to have some internal normal force P, and it's going to act with some angle theta with the horizontal, with that x direction. And on the other side where we made the cut at B, we can have a slightly different amount of tension or internal normal force P, so we get a P plus dP. Now in this string, because we do treat it as typically like a two-force member, we are not going to have any shear force internally, we're not going to have any bending moment happening internally, we just have this tension or this internal normal force happening. And what we're allowing for across this very small length is that the tension changes by an amount dP, and the angle of the string is also going to change by a small amount d theta. And if we look on the left side of the string, that vertical deflection A is going to be some amount W, and because we're only changing a little bit along the length, at B, it's going to have a deflection of W plus a very tiny change dW. Now, all of these dP, d theta, dW terms can be positive or negative. It's just signifying that it's a small deviation as we go from the left side of the cut to the right side of the cut. So we're going to take this free body diagram here and we're going to start getting some equations out of it. So if we look, we can look in this z direction, which is where that vertical deflection is going to take place, and we can sum the forces that are acting in that z direction. So if we see here on the free body diagram of the differential element, in the z direction, I'll start on the right-hand side here, we are going to have this P plus dP force, and in the z direction, we just want that vertical component. So we can take P plus dP and multiply it by the sine of the angle it makes with the horizontal, which we defined as this theta plus d theta. And that gives us the first term when we sum our forces. Then we are going to have, on the left-hand side here, we're going to have this downward P force in this picture, and it's going to be just the vertical component, so it's P times the sine of theta, gives us the second term. And the final force we have here is this distributed load that acts on our string. So we have this f of x comma t, and it's going to act over the length of the string. Now, for this differential element, we are going to presume that the distributed load changes not at all from the left side to the right side. On any one differential apiece, it can be different, but from the left side to the right side of a tiny, tiny piece, we'll assume it's constant. So the force that the distributed load is going to be exerting on the string is going to be its intensity times its length. So its intensity is, for this piece, a constant F, and it's going to be multiplied by the length of the string, which technically is ds, but because of a small angle approximation, we are going to say that ds and dx are equivalent for the purposes of deriving this equation of motion. So the total vertical force is F times dx, the intensity times the length. So the left-hand side here, this is our sum of forces that is happening. And now we have our right side, which is going to be mass times acceleration, because that's Newton's law, F equals ma. So how do we get the mass times the acceleration term? Well, what we're going to see here is this rho dx is the mass of this differential piece of string. Rho is the density of the string, and most importantly, it's going to be linear density as we are deriving this problem. So rho is going to be in something like grams per meter, some unit like that. So mass per length. It is not for strings going to be mass per square length or cubic length. It's just linear density. So if its linear density is rho, we are going to multiply it then by the length of the string to get the mass of this piece of string. And the length of it, again, we are approximating it as dx. So rho times dx is our mass, and then we multiply by the acceleration. We've defined the position, the vertical position or vertical deflection, as w, which can change in space and time. It changes with x and it changes with t. If that is our position or our deflection, we can take the second time derivative of it, and that will tell us the acceleration. So I want del squared w del t squared to get the acceleration of this particular length of string. And keep in mind these are partial differentiations because w is a function of two variables, where I am along the length of the string, x, and where I am in time since I started, t. So this is only a partial differentiation with respect to t. So we are going to be assuming small angles of deflection as I alluded to earlier. So if we assume small angles of deflection here, if we say theta is small and therefore d theta is going to be even smaller, we're going to be able to make some linearization approximations, similar to what we've done in previous units. So this sine of theta term with a small angle approximation, the sine of theta and the tangent of theta as theta approaches 0 is going to become approximately theta, as long as theta is being measured in radians, which we will strictly be measuring it here in radians. And theta is also defined as del w del x. The first spatial derivative of w is going to tell us the angle that the string makes with the horizontal at every point. And if we do the sine of theta plus d theta, again, because they are both going to be small, d theta even smaller, we're going to be able to also make the linear approximation for this term. But before we do that, this d theta term, we can rewrite using a partial fraction. D theta is going to be the same as del theta del x times dx. And we'll be using that substitution idea several times as we go through these derivations here. So the d theta becomes del theta del x dx. And because of the small angle approximation, we can say that the sine of this term is approximately just this term inside. So here also I've substituted in for theta the del w del x, and here the del theta del x is going to give us then the second derivative of w with respect to x, and then that dx is going to come along with it. So we can take this linearization, this small angle approximation, and we can substitute in the sine theta term above and the sine of theta plus d theta term in above as well. If we do that substitution, then we get this longer term that we have down here. Here I have this dp term. I'm going to do basically the same idea I used up here on this d theta term. I want to rewrite that dp as del p del x times dx. So I'll be ready for my next step. So I still have here this binomial times a binomial. I will start to reduce this and simplify it going forward. So what can I do with this equation from here? All right, so copying where we left off here, what I want to do is I'm going to FOIL. I'm going to multiply this binomial by this binomial and get a bunch of terms as I have here. So I've expanded it out, but as I look at the equation I have once I've expanded it, I have at least this term and this term are going to cancel each other out, and the remainder of these terms I'm going to be able to rewrite in a little bit more pleasant way to look at here. So I've rearranged the remaining terms and just put dx's at the end of some of these multiplications, and now I can see that I have some common terms here. Every one of these terms here has a dx in it, so I can actually divide through by my dx's. And what I see here is I have a dx squared, so I'm going to be left with a dx to the first power. And now I can rewrite it without those dx terms since I've canceled them all out. Now, I'd still have one term left here with a dx, and everything else here does not have a dx. So what I can do is a little bit of cheating and say, because dx is going to be a really, really small term, that third term here, this del p del x term, d squared w dx squared term, is going to be really small compared to everything else in this equation. So I'm going to say that this term is going to go to 0 because dx is so small compared to everything else in the equation. So if I get rid of that by arguing that dx is really small, then my terms are going to reduce even further. So finally, I can rewrite this one more time. I have this p del squared w del x squared term. I have a del p del x del w del x term. And for purposes we'll see in a moment why I would want to do this. I can use product rule, although product rule in reverse, to rewrite these first two terms. So I can group these together as the operation of d dx of p del w del x. So we see if we actually went in the opposite direction, if I expand out this product rule, remember product rule is going to be the derivative of the first term times the second. So that's actually this term over here, del p del x, and I copy del w del x, plus the derivative of the second term plus the first term. And that's what this is here. So p, it gets copied, and then I apply this del x to just the omega term. So I can rewrite this line here using this product rule in reverse. And then the f comes along. I will explicitly write it again here as that it's a function of x and t. And technically, that density of the string could change with space if it's a non-homogeneous string. And it could also change in time. So let's say maybe there's a temperature change. Maybe the density of the string is changing. So this is kind of worst case scenario for how many things could be changing in our string. So taking this, and I'm going to make some now limitations on how we can use this solution. I've already had a limitation that we were assuming small angles of deflection, but here I'm going to make some further assumptions. I'm only going to be analyzing or able to analyze strings where the tension is constant. And furthermore, we're going to have uniform material, and we are only in this course going to look at free vibrations. So what simplifications does that give for us? Well, if it's a free vibration, this term is going to be 0. For a uniform material that it's uniform not only in space and time, then rho is of xt is just rho. It's just going to remain a constant. And if we have constant tension, that means the tension is not going to be changing in space or in time. So that means that this p can actually come outside of this differential because it's not going to be a function of x. It's going to act as a constant term. So what does that let us do? It lets us rewrite that equation much more simply as this p del w del x squared equals rho del squared w del t squared. So the last thing I can do with this is I'm going to combine, since p is a constant and rho is a constant, I'm going to combine them on that left-hand side. So what I'm left with here is what I'm going to be calling c squared del squared w del x squared equals del squared w del t squared. And then this c term I am going to be able to calculate as the square root of the tension over the linear density. Again, for these string problems, keep in mind that rho is linear density specifically. So if we see what's highlighted here, what do we have left after all of this derivation? This is the equation of motion for this string. Again, under these circumstances here and limitations that were outlined above, it's for a constant tension string with a uniform material that doesn't change in time, its properties in time or in space, and is undergoing small angles of deformation, and for free vibrations. So if all of those things are true in our string problem, this is going to be the equation of motion that governs its behavior. And what we see here is we have a differential equation. However, it's not an ordinary differential equation as we've been encountering in the past 2 units. Here, this w that we're going to be solving for is a function of x and t. So this equation is a partial differential equation, and as we're going to see, it's certainly going to be more difficult to solve, but we will be able to, under the right circumstances, get a full solution for w of xt that will describe the deflection of every point on the string at every point in time.